So, hello everyone. My name is Ishan and I'm a second year DSAI major at IIT Roorkee. So, today I'm going to tell you about sparse matrices. What are the problems with sparse matrices? How can we solve those problems? And finally, the most important question, how can we solve a linear system that has a sparse matrix? So, let's see what we will have a look throughout this video. So, first, we will be looking at what is a sparse matrix. The next important part, how to visualize a sparse matrix in terms of a graph or a visual representation. Now, one of the most important questions, why do we need to study sparse matrices for machine learning? What are the problems with sparse matrices? How are sparse matrices stored? What is their representation in a computer to solve problems effectively? And finally, how can we solve a linear system with sparse matrix? So let's have a look at what is a sparse matrix. So basically, a sparse matrix is a matrix in which most of its elements are zero, that are null values. We can define a sparse matrix through its sparsity. So what is the sparsity of a matrix? It is the percentage of its elements that are zero. In this 4 cross 4 matrix, we can clearly see that 11 out of 16 elements are clearly zero. Hence, we define sparsity as 11 by 16. That is approximately 68.75%. Now, how do we visualize a sparse matrix? So basically, sparse matrix is a one that contains many zeros, while we define a dense matrix as which does not. So in the graph here, the dots represent many values which are present in a matrix, basically our data, while the empty space represents null values. So we can clearly see that a lot of area is unmarked, that are that there are no dots here. So through this visualization, we can see the matrix is sparse. It is a representation of a sparse matrix containing about a 10,000 elements, out of which about only 3,000 are unknown zeros. That is, the sparsity is 70%. Now, what is the motivation behind sparse matrices in machine learning? My personal motivation for choosing this topic came from our problem, which was given by the sir regarding the image conversion. So basically, in that, we were getting a matrix which was highly sparse, around 95% or more sparse. So I was facing a lot of problem while solving its inverse or getting a solving the linear system. So I decided to choose this topic. Now let's see its motivation in machine learning. So large sparse matrices are really common in general and especially in applied machine learning. So consider this following example. Suppose you ask four of your friends to give a rating of four different movies from 1 to 5 or 0 if they have not seen it. So you can imagine you can get the following ratings from them. So imagine your first friend giving 0 for first two movies because he may not have seen it, a 2 for the third, and 0 again for fourth. Similarly, Paul, Gabriel, and Charles, your three other friends give different ratings. So this matrix contains one, 2, 3, 4, 5, 6, 6 null values. And it is a 16 4 cross 4 matrix that is there are 16 elements. So this matrix as of now is not really sparse. But now consider if you have 15,000 movies, a size of the Netflix catalog. So I believe all of you must have used Netflix or some other OTT platform. So they contain a lot of movies. So what if you allow different person to give ratings for them? It is really understood that not many of you have seen all the movies. Like mostly people see a few movies, so most of them will give zero ratings. So the metrics will become really sparse, maybe the order of 90% or maybe even more. So we don't really have an idea, but it will be highly sparse. So we can also see some other examples where sparse matrices are really common. For example, consider natural language processing. In natural language processing, we consider a feature vector, which is based of the, you can say, different words. So if we consider a paragraph which for which we create a feature vector, which will give one if the word is present in the vocabulary and zero if it is not there. So if a vocabulary contains a million words, while a paragraph contains about 10,000 words, so the vector will become sparse by on its own. Similarly, sparse matrices are also really common in image data, as was my motivation for the subject, graph data, and many more. Google describes internet with the help of sparse matrices. Consider a matrix element ij. It is not zero if a web page I links to a web page j. And I believe we all know that Google contains a lot of web pages. So what is the chance that a web page, a random web page, contains a link to another web page? It will be near zero. So the matrix will be highly sparse. Similarly, Facebook friend relationships are also based on sparse matrices only. It is also stated in the book Introduction to Linear Algebra. In practice, most large matrices are sparse. Almost all entries are zero. If there are 1 lakh words in a language model, then the feature length has 1 lakh. But a short email message, almost all the features will have count zero, again giving us a sparse matrix. So by now, I believe we might have got the motivation behind this topic of sparse matrix. So now what are the problems with sparse matrix? I mean, it's just another matrix, isn't it? So why are we facing so many problems for it? And why do we need to study it as a different topic? Aren't they just like other matrices? Well, let's have a look then. The main three problems with the sparse matrix is space complexity, that is the amount of space they takes, time complexity, the time taken for solving operations on sparse matrices, and the one of the most important, a lot of sparse matrices are ill conditioned. That is, it is difficult to solve a linear system containing sparse matrices. So let's first have a look at space complexity. A very large matrices require a lot of memory, and some very large matrices that we wish to work with are sparse, as we have already stated this. Like in the Netflix case, our matrix contains more null values than data values. But now, do we need to really store all the null values, as it is inefficient and wastage of memory? Consider here that we have a 3 cross 3 matrix, that is, there are 9 elements. And we all know that one numerical value takes about 4 bytes in computer. So this is 36 bytes of memory for this one matrix. But now we can see only 3 of these values are data values. So effectively, we are only storing 3 into 4, that is 12 bytes worth of memory, while the rest is null values. So do we really need to store these null values? No, we will look at the solution. Yeah. Now, time complexity. Very large matrices require a lot of memory, like we have already stated previously, and we need to work on them. So if the matrix contains mostly non-zero values, then there is no that performing operations across this matrix may take a long time, where the bulk of the computation performed will only involve adding or multiplying zero values together. See, in the last example, we can see most of the values are zero. So consider if we multiply two matrices or we take the square of this matrix like A transpose A. So a lot of values, so a lot of operations will only include multiplying 0 or adding 0 with 0, which is a total wastage of our time and increases the time complexity of our operations. It is wasteful to use general methods of linear algebra on such problems because most of the arithmetic operations take O to the n cube for solving set of equations and for matrices. We all know that Gauss elimination take O to the power n cube for solving a linear system. So is it really worthwhile for using sparse matrices which contains more zero values, such operations? Or should we use a different representation? We will have a look on that. Now, ill condition. It is not necessary, but a lot of times sparse matrices are actually ill conditioned. Ill-conditioned sparse matrices are highly sensitive to small changes in their non-zero value. We define a condition number for this. I believe a lot of you might have already known that, which we define as the largest eigenvalue upon the smallest eigenvalue. So if the condition number is large, we define the matrix as ill-conditioned. A small perturbation in the matrix can really change our results. So solving linear systems, performing numerical computations which involve ill-conditioned matrices can be really challenging. Standard numerical methods may struggle to produce reliable and accurate results, leading to slow convergence or divergence. So I think by now we have understood what are the basic problems with sparse matrices. First, yes, they take a lot of space. Second, they take a lot of time for performing calculations, which basically involve just adding or multiplying zeros. And third, there is a high probability that they may be ill-conditioned and we may not get really accurate results. So now, how to solve the problems? We can say we can solve the problem of space complexity and time complexity by changing the representation of our sparse matrices. So let's have a look on the different representations. The first is compressed sparse row or the compressed row storage. The second is compressed sparse column. The third is coordinate list. And the fourth is dictionary of keys. So what is compressed sparse row notation? In this notation, we have three values with three columns. What is the value? The value contains our all the non-zero elements of a matrix. The second is the column index. This 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 column will contain the column index of the non-zero values. And the third is the row. So basically, this will contain the cumulative amount of number of non-zero elements present up to the ith row. So consider if we describe it as a matrix with three columns, and if it is on the, we can say, row I, this is the ith row. So that this column will contain the number of non-zero elements in the matrix up to row I, not including row I, but the number of non-zero elements up to row I. Similarly, compressed sparse column is basically similar to the above method only, but the difference is here the cumulative amount is stored in the column and the row indices is given for the values. The third is coordinate list. It basically just stores the column value, column index, the row index, and the value, just like coordinates. Dictionary of keys is also quite similar to coordinate list. Dictionary of keys just consider there will be a dictionary maintained. The dictionary will contain the column index and the row index, which will be mapped to the value. Just like a coordinate list, the difference between them is really less. In practice, we generally for efficient multiplication, we generally use compressed sparse row and compressed sparse column methods in machine learning. So let's do an example and convert this matrix into CSR format. So let's see, this will be, consider this the row column. This is the column which will store the column index, and this will be the value. So the first is in this row till this is the row 0. So up to above row 0, sorry, there are no non-zero elements. So this will be 0. And remember that while using this, we use the zero indices notation. So the column for this is 0 and the value is 1. Now we go to the next row. This is the first row. So above first row, there is only one non-zero element. So we define it as 1. The column for this is 0, 1, 2, 2, and the value is 3. Similarly, for this one, the above rows contain two non-zero elements. So it will be 2. The column will be 1, and the value will be 2. Hence, now we have converted this into the compressed sparse row representation. Later, we will also have a look at the codes. There will be, we will show that our result is accurate by confirming it with the help of a code. Now, if your concern is efficient modification, like you want to modify your sparse matrix, so basically use dictionary of keys, list of lists, or coordinate list methods. These are typically used to construct the matrices. Now, if your concern is efficient access and matrix operations such as matrix multiplication, so use CSR or CSC format. CSC format. Now, I have already now told you about the representation, but do they really make a difference? Let's have a look at a real world application. Here we are comparing the memory usage of a sparse matrix in dense format and a CSR format. We can clearly see CSR format saves memory. The sparse matrix is around somewhat 40, while the matrix is about 150. The amount of space that we have saved, it's nearly 3.75 times. That is, the sparse matrix is taking 3.75 times less space than a dense matrix, which is really a saver for us and can save a lot of memory. Because in real life, a lot of matrices are just sparse. Now, do they really save time also? Well, I ran a code for training a machine learning model. The machine learning model was for a logistic regression model, and I compared the time used for CSR format as well as for the dense format. So dense format is taking about 0.61 seconds somewhat, while the CSR format just takes a little above 0.02 seconds. So what is It is somewhat around a lot of like 0.16 upon 0.02. That is 8 times less time. So the CSR format is 8 times faster. Also, a lot of machine learning models, such as logistic regressions, are specially designed for CSR formats. They contain special methods for CSR format and saves a lot of time. Also, in my practical application, when I was running codes, I found that if this matrix is more than 70% sparse, the time then we can really see a change in time. Below 70%, the dense formats takes less time and the CSR formats take time. So before using these formats, remember if a matrix is only 70 or about 80% sparse or more, then only use these two representations. Then we can see real memory save and as well as saving over time. Now the question, how to solve linear systems? By now we have seen we can how to solve the problems of space complexity as well as time complexity. But our main question in linear algebra is how to solve a linear system. How can we solve that image problem that we had? Let's have a look. So I will show you four different methods as well as show you the related codes for them. So the first is dimensionality reduction. A sparse matrix can have really a huge number of dimensions. But as we already know, most of those values are just null, null, zero, zero, and zero. So do we really need to take into account these many vectors or these many dimensions for a matrix? No. So what we can use? We can use truncated singular value decomposition. So when working with highly dimensional sparse data, it can be helpful to use dimensionality reduction techniques such as truncated singular value decomposition to reduce the number of features. When working with high dimensional sparse data, using SVD can reduce the dimensions and reduce the number of features. So it will help us in solving the problems. To know more about SVD, we can also look up to other videos. So this was the first method, dimensionality reduction. The second is Tikhonov regularization. Let me give you a basic intuition for this method. So what this basically is, Moore pseudo inverse. This is the pseudo inverse. What we are doing is basically we are adding a regularization constant h square along with the identity matrix. We are adding A transpose A plus h square I. In case of sparse matrices, pseudo inverse generally doesn't work. So what we are doing is basically we are adding h square I as a regularization factor. What it will do is it will reduce the ill conditioning of the matrix. That it will make the condition number more stable. That is, the eigenvalues will become better. Lambda 1, lambda 2, all those eigenvalues will become better. And also it will provide small perturbations in the sparse matrix, reducing the sparsity along the diagonal columns. So basically, this method will reduce the ill conditioning of our matrix, provide us a better condition number so that we can find the inverse and solve the problem. But this will be a direct method. In practical, we use an iterative method to solve this method. So xk, for the kth iteration, we use k minus 1 iteration plus our this our regularization constant, where RL is defined as the residual, but difference between these two. Also, our base case states that we take as y as 1, or we can take y as anything, and then we can solve our this iterative method to get our x. We can define some threshold that when these values become less than this will be our answer for a certain level of accuracy. The next is super LU. I believe most of you will be familiar with the LU decomposition method. So in LU decomposition method, what we basically do is we decompose our main matrix A into L and U for solving the system. So but this method is generally not good for a sparse matrix. In case of sparse matrix, L and U contain a lot of non-zero values for that which take a lot of space as well as time. So space and time will cause our problems as it will increase our space complexity and time complexity. In case of sparse matrix, what we do is we define LU for this matrix. So what is this? A is our main matrix for which we are trying to solve the system. L, DR and DC provide sustainability, or we can say equilibrium to the A matrix, while P, R and PC are the permutation matrices. They help in increasing the sparsity in L and U, while D stabilizes our system for A. DR and DC are two diagonal matrices. The intuition for this method, you can say, comes from like we want our L and U to be more stable and sparse. So just like A. So what will D and DC do? They will stabilize our system for A, and PR and PC will introduce sparsity in L and U. So what we will do is multiply original matrix on both sides by diagonal matrices DR and DC to equilibrate the system. Use permutation matrix P to permute the rows and columns of the scale matrix. We know that diagonal matrix basically scale our system. So DRDC will be scaling and PR and PC will be permuting them for sparse matrices. So then what we can do is we can just take the inverse. Like if the system is like AX is equal to B, so what we want is A inverse P, isn't it? So what it will lead us to, uh, sorry, there's a loss of space. Like it will be B, then it will be PC, then it will be DC, then there will be U inverse, then there will be L inverse, then there will be DR, and then will be PR. And in this way, we can get our X and we can simply solve our system. So this was our super LU, or we can say super nodal LU method for solving a linear system. The final is the conjugate gradient method. So conjugate gradient method is an effective method for solving large, sparse, symmetric, positive, definite systems of equations. It is an iterative method. It is somewhat like the gradient descent. So what we do in gradient descent is basically there is contour and we move down the hill. But in conjugate gradient method, the main intuition behind this is that every direction we move is conjugate with respect to it. So what do you mean with that two directions are conjugate to each other with respect to A matrix? Assume this is direction PK, this is direction PJ. So what do we mean by conjugate is that PKA PJ is equal to 0. This is what we mean by conjugate. Here R is defined as the residual. So the intuition behind this method comes from that the answer of this system is same as this. That is, these two systems will have the same unique solution. So when we define a gradient for this, we will get AX minus B. And we know that it is the gradient is the steepest direction. So we move negative of this steepest direction. So residual is defined as the negative of this. We can see that B minus AX. While P provides us the direction of this. What I am providing you is a high level overview of this system, of this problem. Otherwise, it is a lot difficult to make it understand. So this is our main algo. What it states, we defined alpha. Alpha you can say as the learning rate, or we can say the steps which we take in the direction of P. So we can see we are updating x as xk plus 1 is equal to xk plus alpha k pk. P is just a linear combination of the residuals, that is R, as well as a combination of the previous pk minus 1 iteration, any previous directions multiplied by a factor of beta. So we need to make ensure that P's are always conjugate and while R's are always orthogonal to each other. That is, when we move in a direction, it is always perpendicular to the previous direction. So we are defining A as alpha as RT, R transpose R upon P transpose AP. And then we are updating R as RK minus alpha K APK. So if our residual becomes less than a certain threshold, we can say that our system has converged and we can exit the loop and get the solution. Beta is defined as R transpose K plus 1 iteration, RK plus 1 upon R transpose K. And we can define P as a linear combination of R as well as previous PK, and the loop continues until we have found a residual less than our threshold. So this was basically our conjugate gradient method, in which we are making sure that the direction we move is always perpendicular to the previous direction so that we don't backtrack ourselves. And it is faster and better than gradient method. So why is it really good for sparse matrices? So one of the main reason it is good for sparse matrices is because what we are basically doing it is that we are just multiplying, we are taking only matrix multiplications. So matrix multiplications are good for us because our libraries have been really designed for efficient matrix multiplications, as we have seen in the previous slides. The time complexity becomes really less in case of CSR format. So what we are doing is matrix multiplication, again matrix multiplication, simple matrix multiplication and addition, subtraction, multiplication. So these are very really efficient algorithms for us. And also this also preserves the sparsity of the matrix. So these methods are really good for sparse matrix. So with this, the theory part is complete. Now I will show you the code. So now let's have a look at the code. So first we are importing all the libraries that we need. Matplotlib as PLT. We are importing sparse from SciPy, NumPy, CSR matrix, random, system, logistic regression, time, truncated SVD, CSE matrix, SLA. SLA is nothing but for super LU. So let's first look how did we visualize our sparse matrix. So we created a random sparse matrix with density 0.1. Basically, density 0.1 means that our sparsity is 1 minus density, that is zero point 0.9, that is 90% sparse matrix. So we basically plotted it like this. You can see it is similar to the graph which I had shown you in the videos. So again, these dots are the values and the rest of the area is our null. Now, how do we convert to CSR format? So you can see what we have, the NumPy library already contains a direct method for converting a matrix into a CSR matrix. Just we have to call sparse.csr matrix M. With this, we can convert any matrix to a sparse representation for CSR format. And we can see the answer is correct and we can compare it to our result. Now, we are comparing CSR and dense formats in terms of space and time complexity. So this is the memory usage comparison. Here we are defining a matrix of 1,000 cross 1,000 with sparsity 95%. So number of non-zero values, we can get it through this. This is the code for getting the number of non-zero values. And now we are randomizing our row indices as well as column indices in the matrix where our non-null values or data values will be present. Through this, we are forming our sparse matrices. These contains our non-zero values, which we have created through this random function. This is the row indices as well, column indices, and the shape, number of rows, number of columns, that is 1,000 cross 1,000. Now we are plotting this. For that, we are using two labels, that is dense matrix and sparse matrix. Sizes, we are getting sizes using the system library of Python, that is sys.get size of sparse matrix to dense as well as sparse matrix. This will provide us the size of the dense matrix. This is providing us the size of the sparse matrix. And now we are plotting it. We can plot this using the PLT. So we can see how much the gap is between them. Sparse matrix takes considerably less space than dense matrix. Now we are comparing the time for training our logistic regression model. Consider that we have 10,000 number of samples and number of features are just 1,000. So sparsity will be 0. We are considering sparsity as 95%. So x is equal to random. We are making a random sample and y is also random. Y will be our target vector. Start time, we are taking using the time library for starting time. We are fitting in the logistic regression model. So, and we are getting the training time using the current time. This gives us the current time minus the start time which we have stored. Similarly, we are doing it for the dense matrix also, and then we are plotting this. So this gives our CSR format time, this for our dense matrix, and there is a considerable difference between them. Now, how to solve the systems? Code for truncated SVD. So the Python library directly provides us truncated SVD. We are using a truncated SVD transformers and we want the components to be 10. That is, at the end of the feature, we only want 10 main components for us. We reduce it by fit transforming our matrix into the truncated SVD transformer, that is SVD, and we are printing X as well as reduced sparse matrix. This will be our X and this is our reduced sparse matrix. You can clearly see it is much smaller than this. For this, we are actually need to open another text editor while we can nearly see all of the metrics here only. So we can already see how much the difference in size is there. So we have actually reduced the dimensions and now we can use it for solving our systems. The next is our super LU method. So SLA provides us a direct SPLU, that is super LU method for A. A is our sparse matrix in CSC format. Now here we are using compressed sparse column, not row. SPLU is basically optimized for CSC method. So it will be better to use compressed sparse column method. B is our AX is equal to B, so output X, we are using X for solving. X is equal to LU dot solve P. PR is our permutation matrices, PR, PC, which we can get through these two codes. And we are printing them as LU dot and A dot X gives us back our main B. It proves us that our solution is correct. Our X is this, and these are our permutation matrices, which we can get in their correct form using these two codes, PR and PC. Now this is our conjugate gradient method. So basically we can get any array, we can change it to a sparse array. Consider it like a sparse matrix. What I am doing now is creating a sparse matrix and we can define our B of the same size of 3. First, we need to run all the libraries above. Uh, there's some small error. Oh yes, so what we are so this was what we had to initialize at the starting. So X is our original X node. So we are initializing X as 0. This is our A, our sparse matrix. This is our B. This is our original initialization. This is R, the first residual. So B minus AX. This gives our R node. At first, we are initializing P, our direction as R node only. We are defining as number of iterations as 10. This method generally produces a good convergence in just a small number of iterations. This is storing our X and R so that we can plot it down here in the graph. You can see basically after only 2 iterations, our values get constant and with the residual gets 0 after only 3 iterations. So now in this loop is our main code. We get our alpha R transpose R upon P transpose A P. Next we change our X according to alpha is you can say our step size, P is our direction, R new R minus alpha dot NP dot AP. Then we define our beta for defining our next P, that is R new plus beta into P. So P is just, we can define it as linear combination of residuals as well as previous P's so that they are conjugate with respect to A. And residuals are nothing but just gradients, negative of gradient at any iteration A, K. So we define R is equal to R new, we append them into the history, and then we are plotting it. So with this, we can say now we have a good knowledge of what are sparse matrices, how we can visualize them, how they are represented, how we can solve linear systems in them, and how to solve the systems. So with this, I end the video. Thank you.